Welcome to Study Loop.
We have in this case a liquid fuel mixture that is composed of three main components. 30.35% hexane, which is C6H14. We've got 15.85% heptane, C7H16. And then the rest will be octane. So let's figure out how much octane there is. 100 minus 30.35 minus 15.85 is equal to 53.80%. So we'll put that one up there, 53.80% octane. Now, we have 10 kilograms of this blended fuel, and we want to know how much carbon dioxide is produced when the entire thing is combusted. So let's start with the first one, which is hexane, C6H14. Now, best way to start this, of course, is we need some stoichiometry, and all stoichiometry must begin with a balanced equation. So we'll put up C6H14 reacts with oxygen, and whenever a hydrocarbon is combusted, we'll always get the same two products, CO2 and H2O. Now let's balance. The best way to balance is to take the subscript on hydrogen and put it in front of the water. Adjust the hydrogen next, adjust the carbon next, and then close out with the oxygen. Looks like we have 24 and 14. Which is 38, and half of 38 is 19. So here's my balanced equation for hexane. Now, we also know that we've got 10,000 grams of fuel, and I know this because we started with 10 kilograms. And here's my metric chart. King Henry died by drinking chocolate milk. And to go from kilograms to grams, we go 3 places to the right. So we'll move our decimal of 10 kilograms, 1, 2, 3, and thus make it 10,000 grams. But that's the total fuel. So we're going to multiply that by 0.3035, which we see here is the percentage of the fuel, that's hexane, and we'll have 3,035 grams of C6H14. So let's begin with that. 3,035 grams of C6H14. We are supposed to find out in each case how many kilograms of carbon dioxide can be made. So first we'll have to convert this into moles so we can see through the reaction how far it'll go. Now, the molar mass of C6H14. There's 12 grams per mole in each carbon atom because of the periodic table's atomic mass. Multiply that by 6, plus each hydrogen is 1, but there's 14 of them. Add it all up, and we'll get 86 grams of C6H14 for every mole of it. Now we'll use our balanced equation coefficients to find our mole ratio. There is a 2 in front of the C6H14. So for every 2 moles of C6H14 that react, and we're looking for carbon dioxide, there's 12. 12 moles of carbon dioxide that react. And then we'll close off with the molar mass of CO2. So let's calculate that. Carbon again is 12, oxygen is 16, but there's 2 of them. Add it all up, and we'll get 44 grams of CO2 for every mole of it. Let's check to make sure that my units line up correctly. Grams of reactant, cancel. Moles of reactant, cancel. And finally, moles of carbon dioxide, cancel. We will find grams of CO2 that form here. Alright, now, when this is calculated out, we will find that this amount of hexane will yield 9,317 grams of CO2. Next up, we're going to calculate the same thing for heptane. So let's lose this equation, and we'll calculate out the new one. Now in this case, we've got C7H16, but the rest will be the same. It reacts with oxygen, forming the familiar hydrocarbon combustion products, CO2 and H2O. Let's do the same trick we did before. We'll put the subscript of hydrogen in front of water, and from there, because we now have 32 hydrogen, we'll double this. We now have 14 carbon, so we'll fix that. And now I've got 28 and 16 . 28 and 16. That will equal 44. So we'll put a 22 here. And now, this trick, we still have to correct it because every one of our coefficients is divisible by 2. So we're going to divide all of them by 2. We'll get rid of that one. We'll change this 22 to 11. We'll change the 14 to 7. And finally, we'll change the 16 to 8. And this will be our balanced equation. Now, like before, we have our 10,000 grams converted from the 10 kilograms of fuel, but 15.85% of it is this heptane. So again, we'll take our 10,000 grams times 0.1585, and that will equal 1,585 grams of heptane. So let's lose this part of our equation, and start over with our new one. So we've got 1,585 grams of C7H16. Let's once again calculate a molar mass. Now, carbon is 12, and there's 7 of them. Hydrogen is 1, and there's 16 of them. Add it all up, what do we get? 100 grams of C7H16 for every mole of C7H16. Next up, we need a mole ratio. There's no coefficient, so 1 mole of C7H16 for every, what are we looking for? Again, carbon dioxide. For every mole, for every 7 moles of CO2. And then we'll close off with the same thing as before because the molar mass of carbon dioxide does not change. When we take 1,585 times 7 times 44 and divide it by 100, we will find that the heptane component will produce 4,882 grams of carbon dioxide. Alright, so we've got 2 parts of our fuel done, and now we're going to go on to our third, which is octane. So let's lose all of our stuff here again and write a new equation and component for octane. So octane, C8H18, when it burns in the presence of oxygen, familiar products, CO2 and H2O. Great. Alright, we've got a subscript of 18, so we'll put an 18 in front of the H2O. We'll fix the hydrogen on the left. Now we've got 16 carbon, and then we've got 32 and 18, which equals 50. Half of 50 is 25, thus satisfying our balanced equation. From before, we know we've got 10,000 grams of fuel, and we'll multiply it by the decimal form of the percentage, thus equaling 5,380 grams of C8H18 is what's going to combust. Now, from there, we will calculate the molar mass. So we've got 8 times 12, so there's 8 carbon, and there's 12 grams per mole, plus 18 times 1. That will equal a molar mass of octane of 114 grams in every mole of it. From there, we know, according to our balanced equation, that 2 moles of C8H18 react every time 16 moles of CO2 will form. Once again, we can finish off with the same final step because the molar mass of carbon dioxide will not change. Now, from there, we've got to multiply 5,380 times 16 times 44 divided by 114 divided by 2. And this will come out to be roughly 16,612 grams of CO2. So, when this fuel combusts, all 3 of these products are going to result because they're all burning at the same time and they're all being consumed. If you add all 3 of them up, you will roughly get 30,800 grams, but the answer was requested in kilograms. So if we have our metric chart up again, and we move back to kilograms, we'll move the decimal back, and our final answer will end up being 30.8 kilograms of CO2, of carbon dioxide, will form from the complete combustion of this blended 10 kilograms of fuel.